my presentation is simply a simple example to illustrate in detail on his presentation or his future view on the LE and security. So this is integration on the security issues and IoT. So, okay, I don't have much time, so that I need to go through. So first of all, we have a simple introduction on the background and the motivation of our work, and then the proposed scheme and conclusion. So the target system is a so-called 6LoWPAN. What does it mean? 6LoWPAN means that it's 6 means that IPv6, which, as David mentioned, that it is in the future it will be used as an IP layer protocol, so that 6 indicate that's IPv6. LoWPAN means that low power personal area network. Okay, so this is supposed to be a new network which developed by IETF, the Internet Engineering Task Force, and it has been standardized. Basically, as a physical layer, it is nothing but defined as IEEE 802.15.4, which basically traditionally it is called ZigBee. Over that is the medium access control layer, which is going to have the control on the medium access. And between the IPv6 and medium access control, there is a so-called adaptation layer. This is totally new, which defined for the 6LoWPAN to get connection with IPv6v4. So above it, transport layer, application layer as normal, which we use over the IP layer, IPv6. So basically, in fact, this system has a physical layer specified by 802.15.4. Same thing for the medium access control layer, and one special thing is that the adaptation layer to get connection between IPv6 and the MAC layer and the physical layer of the big ZigBee. So this is our entire stack of the 6LoWPAN network. So this is the stage for all security scheme to put in. In fact, we have designed a security scheme which is located at the medium access control layer. Okay. The other issue is mobile IP. So IPv6 will be integrated into the this 6LoWPAN network, while there are some proposals to say how about if the sensor node is going to move, such as the sensor node equipped on robotics. The robot may have a lot of sensors on its body, so that if there is a movement of the robot, then the sensors on entire body will basically move. So that how about the support of mobile IP? So mobile IP is not new concept, which has already proposed for the Internet Engineering Task Force, and it's already to allow mobile device to move from one network to the other. So this is basically this is the infrastructure for the mobile IP to move. Normally, there is a home network, while when it moves to another network, it is called a foreign network, and so on. So since mobile IP has used the IPv4, later on there's a proposal to propose the PMIPv6 IPv6, that is to equip the mobile IP with IPv6. This one has been proposed to support mobility management without the involvement of the mobile node. Basically, it can be done by the routers. So in this piece of proposal, there are a lot of issues that has been involved. First of all, the gateway. The gateway is called the mobile access gateway, and further in the backbone network, it has a local mobility anchor, and further to the corresponding node. So that any mobile node moves from one network to the other network will basically go through under the control of a mobile access gateway. Let's call it a MAC. And then to move to the other network, and then the IP service will be still there. For this PMIPv6, basically to improve the performance of the IPv6 mobility with the ability to reduce the loss rate when the information exchange. Then there will be an issue that to achieve fast handover, because it is from one domain or under the control of one MAC to move to the area controlled by another MAC, there will be a handover happen. So that in order to control the switching of the communication, or we said that it is a handover, fast and localized, and PMIPv6 has been proposed. So basically, it is to support the handover and increase the speed of handover, reduce the latency involved in the handover. Also, there are some other proposals to enhance the PMIPv6, basically to reduce the latency involved in the handover to achieve faster handovers. So some other proposals also have been proposed in order to improve the performance of the handovers which controlled by mobile IPv6. However, all of the work have not addressed the security issues. So we found a very few work on the security, which is the one proposed as the PMIPv6-based authentication schemes. There are some, let's say the reference 7 to 9, have a proposal for the, for the vehicular network, but it is not for the 6LoWPAN network, as we mentioned at the beginning, which is supposed to be the workspace which we work on. So that there are some kind of PMIPv6-based security scheme, but they are applying to the vehicular network. So in that proposals, they are talking about how about the authentication from the control of one MAC when the vehicle comes into the area of controlled by another MAC, handover has to happen. Then how about how to ensure that it is not a fake vehicle to come into the coverage of the MAC. Recently, there is a proposal it is called the Secure Fast Handover Mechanism for PMIPv6 network. And it can achieve the goal that to reduce the latency in the authentication process, provide the security functionality to the handover process, so that to guarantee that the operation of the authentication will be free from some kind of attacks. However, we have disclosed that it suffers from replay attacks. So that suffers from replay attacks and impersonation attacks. So that it's still quite vulnerable. And also another work which has been called as spam, also to propose to enhance the previous work. And however, the issue is that the computation overhead will be made low, but they still have some security vulnerabilities. We have disclosed that one of the vulnerabilities that the nonce side in the process of the authentication cannot be verified whether it is a new one or not, so that it has lost the freshness of the nonce, which are supposed to be associated with the timing. Secondly, one group key has been shared by all the mics, since we know that the mic is going to the control of the mobility of the, the mobile sensors. So that some of the confidential parameters are easily to be disclosed. So that that will provide the space for the attackers to attack the system. So that based on this discovery, we propose a new scheme, which is based on the spam, okay, to intentionally to protect the system to avoid these two shortcomings. So it is supposed to be the motivation of our work. Okay, so that our work is basically based on PMIPv6-based network. It is called Secured Mobility Scheme. So we name it as PBSMS, designed to provide more secure protection over the, over the authentication process to protect the 6LoWPAN network, for the mobility issue. At the same time, try to reduce the handover latency in order to, to improve the performance. The reason for that is that all the sensor node, which are called the 6LoWPAN node, will not have enough battery, will not have much, computation resources, including the ability of the computation and also the memory resources. So that they are supposed to be resource-limited devices. So that we need to design a scheme which to protect the security, to provide the security while at the same time try to reduce the resource used for the protection, for the involvement of the security functions. So this is the motivation which we are going to attach to work. By the way, the critical issue inside the design, or the core issue of the design is the LMA, which is a local mobility anchor, is going to share with the 6LoWPAN mobile node with a shared key chain for secure communication purpose. Just the AA server only needs to perform full authentication procedure with the 6LoWPAN mobile node in the certain period of time. For example, in the beginning of the node to join the network, or after a period of time to refresh the key chains. So when the 6LoWPAN routers in the network to significantly reduce the handover delay. Besides, since the 6LoWPAN, as I mentioned, the mobile node has limited resources, or simple, we can only use the simple cryptographic operations to protect the transmission message. So that we have considered this kind of thing to make the the proposed scheme to be efficient with less resources required. So this is the system architecture we have built, which consists of 6LoWPAN mobile nodes, and also mics. We call it 6LoWPAN mic. And local mobility anchor still there, which is same as before in the previous network, and AA server, which provide which serve as a third-party authenticator. So those are the explanation on each of the components inside the network we have built up. And further, we have, based on the assumptions we have designed our secured authentication protocol. So what are the assumptions? We see that LMA and the AA server are supposed to be trusted in the backbone network. So they are supposed to be connected by cable without ability for the attackers to attack them wirelessly. The 6LoWPAN mic are connected with LMA through also cable, so that with a high bandwidth while low bit error rate, without much vulnerability to be attacked. The reason is that we assume that they are connected by cables. Just the 6 mics and the LMA are mandatory to implement the Internet protocol, which is IPsec. That is normal, which is used in the current Internet to protect the security. Well, what we have done is that we design the security protocol over the 6 mic and the mobile node in order to protect the mobile node to get a connection with a 6 mic while switching the control of the communication when the 6 mobile node move from one area to the other area controlled by another or target 6 mic. So what is the attack model? We see that we still work based on the so-called Dolph-Yaw intruder model, which is a very common model used in the current research of the security. So we say that based on this model, the attacker may be outsider or insider in the system, which can drop any message transmitted through the wireless channel, not from the cable channel. Messages can be decrypted or encrypted if the attacker obtains the keys. So that if the attacker has the key, then everything is compromised. No security anymore. Messages can be changed, constructed, decomposed, forged, injected, or replayed, and to send to any legal entity, or let's say the 6 mic or the mobile node. The attacker can impersonate a principal to communicate with the legal devices. However, it is assumed that they have so strong ability, we still assume that the attacker is unable to guess a nonce, which is selected from a sufficiently large space. So it's quite difficult, not able, but quite difficult for the attacker to guess the nonce. The attacker also cannot retrieve all the information from a given cyberattack or generate a valid cyberattack from a given plaintext without a complete key. So without key, anything cannot be done by the attacker. A private key that matches a given public key cannot be calculated by the attacker. So those are the things attacker cannot do. So we have also some notification defined, including the identity of the mobile node, password of the mobile node, the nonce produced, the timestamp, private key, and so on. And also, we design the authentication scheme in three phases. The first phase is called the initial pre-deployment phase, which is supposed to be the initialization phase. So in this phase, basically, the AAA server will do kind of distribution of the secret information to mobile nodes and 6 MACs and so on. So this is the period for the AAA server to prepare or distribute the keys before the operation of the system. So I'm not to go through the details. So anyway, in the second phase, it's called the initial authentication and key establishment. It is establishment phase. In this phase, the purpose is that we perform the first time of the initialization, while to have the key to be generated and distributed to the mobile nodes, which this process needs the involvement of 6 mobile nodes and 6 MAC in the process, evenly to involved of AAA server. So this is a kind of a process which the system has started to work at the initial stage while there's no handover happens. So when the system starts to work, this work has to be done in the first phase, in the second phase. Then this is to prepare the handovers, to prepare the key distribution, to distribute to each mobile nodes and 6 MAC and so on. So there are a lot of information exchange. First is first message 1, message 2, message 3, message 4, and so on. Message 5, even 8. Eventually, finally to get the key distributed from 6 MAC to the mobile nodes. So each mobile node will be identified as a legal entity inside the system. And this is the phase for the mobile node to start to work or start the operation to prepare. Basically, this is one step to get the mutual authentication between the mobile node and 6 MAC. And it may take time. Anyway, here we have taken too much time, while we'll reduce the time over the handover process. So the third phase is the handover process. This phase will do some kind of authentication, or we say that a quick authentication, in order to reduce the latency which involved in the handover process. So that the work of in this phase can only happen when the mobile node move from the coverage of one cell to the other cell, which is controlled by the target MAC. So in this process, also 7, 8 messages exchange over there. However, this amount of information exchanged will be quite small. There are a few steps to exchange 8 messages. So this is the overall design of the authentication scheme. Basically, there are 3 phases. One phase is that before the system to start to work, the AA server should distribute some confidential information to the mobile node and 6MIC and so on. While the system starts to work, we have the mutual authentication between the mobile node through the 6MIC with the server, with the AA server, and then to let them to identify each other. At the same time, the keys will be generated with the purpose to use those keys we call the session key, which is temporarily used to have the information exchange so that it's possible for the information to protect the information, to prevent the information to be intercepted. So this is kind of a second phase. While in this phase, although the system has started to work well, there's no handover has happened. Basically, the mobile node is basically maybe move in the current cell without go beyond the border of the current cell. While the third phase is that we are going to have production of the authentication process to make it secure so that we come up with the handovers phase. This phase is going to protect the mobile node, the information which is delivered, exchanged during the movement for the current location of the mobile node to the new location which is controlled by another 6MIC. So this is a side of design in order to, systematically protect the 6LoWPAN information, while when it moves from one location to the other location, which is cross the border of the cells. Okay, based on this design, we have done some security analysis. So basically, very, very popular, we use the so-called AVISPA, which is a formal verification to verify the design protocol. And also, we have used the band logic, which is logic language to derive to get the conclusion, says that the two parties could get identified each other to mutual authenticate each other. So we have the tools to prove what we have designed is logically correct. What we have designed is able with the ability to against some kind of normal malicious attacks. We cannot say our scheme is able to prevent all of the attacks. That's not true. As David said, you always behind the attacker. Attacker can think of design, any kind of design, you don't know when it will come, right? So that we just simply verify that our scheme is able to protect the common, well-known malicious attacks. We are not able to detect any kind of attacks. The reason is that you don't know. When a day in the world, everybody is intelligent. Who knows who will design an intelligent attack as the attack model to attack the system. So this is what we have done. We have done this kind of formal verification in the field of research of security using the AVISPA tool. Of course, there are other tools of formal verification. In our other works, we have already used them, such as Sizers and some others. This is an explanation on the AVISPA. In fact, that this is a quite old tool. It's not so perfect. Also, we have some kind of comparison on the security features to compare our proposed scheme with the spam. And then we perform so-called performance evaluation. For the performance evaluation, we do two kind of things. One thing is to simply compare how much resources our scheme is going to use. Compare with the SMIP, so to say that whether our system, our design protocol has much resource to use or not. This is a static, we can call it a static analysis. The other way is that to perform the simulation, that is a dynamic analysis of the performance of the system, of the proposed solution which are operating on the system. So in the design, in the performance evaluation, very interesting is that, in fact, the performance of our proposed scheme is not as good as the SPAN. But our system has, the feature is that when we do initial authentication, we have taken a lot of resources. While we move the handover resources used into the initialization process, so that once we have an initialization and we have many number of the handover process, then it happens that since for each handover process we use less time, we reduce the latency, so that accumulatively, in the long run, that is, for example, once the system has started, it will have, let's say, multiple number of handovers, then the total delay could be reduced. This feature has been presented over this plotting. It says that we have identified the exact number of the handovers. Then after this number of the handovers, we are able to save time. So this is through the simulation we have achieved. So it shows that at the beginning, our scheme has taken a lot of time. Well, after 13th of handovers, you can see that the time used for the handover will be much less on average, which means that although at the beginning we have taken a lot of time, while after 16 times of handovers, this time consuming has been reduced much on average. So this is, say, we are able to produce the authentication scheme with high efficiency. That is a kind of support. But the major objective of this design is going to prevent, to overcome the shortcomings brought by the SPAN. Let's say the one is the confidential information is easily to be disclosed by the SPAN. The other one is there's no freshness of the nonce. So these are 2 points we have already overcome, while we have a little bit better performance than the SPAN. So this is what we have achieved. Basically, we have a new proposal, which is called the PBSMS, to overcome the security shortcomings brought by the SPAN, particularly for 6LoWPAN network, which is supposed to be used in IoT, IoE in the future. So that's all for my presentation. Any comments, questions?